winner is Adidev JE and is also a member of US Space Club. And the first prize has been backed by another member of US Space Club, and he's a very close friend of mine. And he also backs a certificate as well as the first prize of the first cash prize sponsored by Cinderby Nurture. So that is it from the results of UL Space Quiz 19. But before we move into today's long-awaited session, let me take a few moments to remind you about a few very important things that you should be taking care of today. Let me please remind you about the most um, important things that you should keep in mind while you attend today's session. So the most important thing, as I usually say every day, is to keep your mics and your cameras switched off. Do not switch them on unless the speaker or temporarily. So we don't want that to happen. So make sure that you don't present your screens. And if you accidentally do present your screens, make sure that you click on stop presenting at that very instant. And if you have to rejoin at any point, make sure that you click on the option join and do not click on present. Now, there is always a possibility that somebody might present their screens. So in such an occasion, for you to not lose the slides of the presenter, make sure that you pin the screen of the presenter on your screens. So what you have to do is that when Dr. K. Rajiv presents his screen, make sure that you click on the pin kind of icon, which will be visible as you move your cursor or a mouse pointer towards the center. You'll see this pin kind of icon, and when you click on it, you'll be able to pin it on your screens. And if you can't find his presentation anywhere, you can click on the option people, where you'll get the list of all participants, and you can browse and you can find his slides, which will usually be his name followed by presentation, which is written inside a pair of parentheses or brackets. And when you click on them, you'll be able to select his slides on your screen, and you'll be able to pin it. And the third most important instruction is to make sure that you ask your questions first in the chat box. All questions that you want to ask, make sure that you ask them in the chat box. Do not unmute yourself and ask it to the speaker unless the speaker wants you to do so. So what we usually do is that we ask you to post your questions in the chat box, and we select the most relevant ones, and we ask them in the Q&A session, which will follow the long-awaited speech by Dr. K. Rajiv. And for you, you can ask your questions either in English or Malayalam, which is preferred by yourself. But make sure that you type the questions with the alphabets of the respective language that you're using. Like that is, make sure that you write Malayalam questions using Malayalam alphabets or English questions using English alphabets. The fourth important thing is that today's session will be followed by the 20th edition of UL Space Quiz. Now, you might have just seen me presenting the results of UL Space Quiz 19. So after the whole session today, usually at 5 p.m., we have this quiz over Google Forms, which is not compulsory. You may attend it. And the first prize winner will be eligible to achieve a cash prize, which is sponsored by Cinderby Nurture, and the first, second, and third will receive their respective certificates. So your rankings will be based on your score and your time of submission. So the faster, the better. And you have to submit the answers before 7 p.m. tonight. It will be the link for the quiz will be given to you in between, and it will only be open once the whole session has been completed today. So if you want, you can attend it and make sure that you perform well, and best of luck to all of you for that. Another important thing is about Cosmos, which is a platform which is maintained by UL Space Club. So if you are a science enthusiast or a person who is interested in astronomy, you can become a part of Cosmos, where you'll get all kind of real-time updates on our programs, as well as the fact that you'll be able to engage in plenty of beautiful discussions on space facts. So if you are interested, you can DM me or Varun, and our contact numbers will be provided to you in the chat box, which pretty soon by Varun. I think he'll be providing it to you. Another important thing is that you know that this is World Space Week. Every year we commemorate this particular week as World Space Week, and because of that, considering the fact that we are a space club ourselves, we are planning a few important webinars ourselves as well, which will be on the 5th and 7th of October. As you can see, Let me present the screen in a moment. Please wait for a moment. I hope you can see my slides right now. I think Sriram or Varnatan can please tell me if it is visible. Is it?
Yes, Bharat.
Yes, yes.
Yes.
Okay, so you can see this particular image right now. Aren't you seeing the World Space Week kind of thing? Hello?
Hello, yes.
Okay, you can see the World Space Week poster.
Yes, we can see the
Okay.
full poster.
Okay, so as I said, we'll be having a few webinars on the 5th and 7th of October, which are highlighting the importance of satellites in daily life and the role they play in Indian rural and urban life. So the 5th of October, a session will be from 3 p.m. to 5 p.m. and it is based on the topic Indian scenario on environment and sustainable development through remote sensing satellites. And the speakers are Dr. YVN Krishnamurthy, Senior Professor and Registrar, IIST Thiruvananthapuram, and former Director, National Remote Sensing Center, Hyderabad. He'll be accompanied by Dr. K. Ganesh Raj, who was General Manager, National Remote Sensing Center, ISRO, Bengaluru. And we'll also have two of the student fellows of UL Space Club, one of which happens to be myself and my friend Adil Krishna, who will be interacting with the participants so that we can maintain a very lively session. The 7th of October session will be from 3 p.m. to 5 p.m. on the 7th of October, and it is based on the topic Indian strengths in communication, navigation, disaster risk reduction through satellites. And the speakers are Dr. V.S. Hegde, former Scientific Secretary, ISRO, and former Chairman cum MD, Antrix Corporation, Department of Space, Bengaluru. And he'll be accompanied by Dr. S. Rangarajan, former Director, Master Control Facility, ISRO Hassan, and Director, ISRO Telemetry Tracking and Command Network. And the interacting student fellows will be Varun K. Munkundan, whom you've just seen now, and Sriram D, whom you'll be just seeing in a moment. So that is it from the UL Space Week programs. We also have another program under Cosmos. As I've already told you, we have a group of students in WhatsApp called Cosmos, and we have our own programs. And on the 9th of October, we'll be doing our first program, and it is based on the topic The Great Explosion to Vengeful Corpses, and it is led by Abhinand PS, who is undoubtedly a UL Space Club fellow, and he's also an integrated MSc Max student at Pondicherry University, and it will be at 3 p.m. on the 9th of October, and we'll have two panelists from students. The whole thing is done by students, and the panelists will be Varun and myself. So that is it from the most important announcements and instructions from my part. Over to Sriram for the introductory session.
Okay, I think I'm visible and clear.
Absolutely, Sriram.
Okay, good afternoon to all of you. Thanks to Varnatan and Bharat for providing the instructions and announcing the results of the previous 19th webinar quiz. I welcome all the scientists, veterans, teachers, UL Space Club organizers, students, and all other participants to the 20th session of UL Space Club webinar series. We, the UL Space Club, is a foundation under the umbrella of Uralangal Labor Cooperative Society, stands for enriching and flourishing the scientific aptitude of students, especially in space field. Within the 3 years from starting, we conducted many great events physically, that's before the COVID. From the beginning or the initial stage of COVID pandemic era, we start this new venture called the webinar series, which is going extremely well for these past 6 months. Today, in the 20th session, we have Dr. K. Rajiv as the lead speaker on the topic Earth's environment and its diagnosis from space. He's an eminent scientist from VSSC, that's Vikram Sarabhai Space Center under ISRO. As I said in the previous webinar, many of us got the opportunity to visit VSSC. Undoubtedly, it's a fascinating arena for us, the students who are highly interested in space. It's our pleasure and privilege to have an experienced scientist from there itself. He is currently heading the microwave and boundary layer physics branch, that's MBLP, and also atmospheric technology division, ATD of SPL. I welcome you, sir. We have Varnatan, Abhinandatan, and all other core team members here to give you the instruction when it is necessary. And the moderator of the session, our all-in-all Shajil sir, is here to control the session, and he will give the information about our respected speaker. Our chief mentor, Ike Kutisa, the former HRD director of ISRO, is here with us as always. Jaram sir and the whole webinar family, including the eminent scientists all over India, will be with us in this session too. Our student core team is ready to handle the Q&A session after the talk. Damodran sir, the one who plays the major role in connecting us to UL, is here to express the vote of thanks after the session. Our streamer Adil Krishna is also ready, so all set. Without any delay, I welcome the moderator Shajil sir to take over the session.
Thank you, Sriram. We are continuously sitting in this webinar series for the past 140 days. We already passed 140 days, and we forget about the pandemic happening here. Before the scientific group is using these technologies, we use this Google Meet to deliver the field of science to the students, and we have more than 100 students continuously watching this program, and that's their enthusiasm maintains or make us more thankful and grateful to these occasions. And today we are discussing on Earth environment and its diagnosis from space. And we have a 480 kilometer high atmosphere on this Earth. That atmosphere make this Earth a livable or living area for the beings on this Earth. And that's a secret that gives us the warmth and that maintains the climate and everything on this Earth. And even life is possible on here. And we have an eminent scientist from VSSC, Vikram Sarabhai Space Center, Trivandrum, to speak on this atmosphere and its observation and its analysis and its interpretation of things happening by using technology that the data we receive from the satellites. That's only because of the space exploration we are able to predict what will happen tomorrow. And today we have Dr. K. Rajiv, a scientist G, head of MBLP Space Physics Laboratory, VSSC, Trivandrum. And he is part of ISRO in 1993. And he joined in Vikram Sarabhai Space Center in that year. And he's a postdoctoral research physicist at Scripps Institution Oceanography, University of California, San Diego. And this week also he released an ISRO Story of Week based on his paper on tropical clouds. That means he's continuously searching for what will happen on these clouds and climatic change happening in this world. And in 2001, NASA Earth Observatory did a press release as breaking news based on his paper on aerosols over Indian Ocean. That was also a wonderful findings, and that catch eye of all scientists all over this world. And he's a recognized research guide at Kerala University and CUSAT, and his areas of research include atmospheric physics, remote sensing, aerosols, clouds, and climatic change. And he published over 70 research papers and peer-reviewed international scientific journals. And 4 researchers obtained PhD under his guidance. And now he is showering his blessing and his guidance to the researchers who are in the field of science and especially in the field of atmosphere. And currently he is heading, as our Sriram told, Microwave and Boundary Layer Physics Branch, MBLP, and Atmospheric Technology Division of SPL, and is the principal scientist of National IGP Nobel Project and chair SPL Academic Committee. And he is an advisory committee member of Indian Institute of Geomagnetism, Mumbai, and several national level scientific committees. And he is reviewed. He expressed his presence in several international journals in atmospheric science. Now, sir, we are all searching and looking for what will happen tomorrow. Yes, the climatic change is hitting our Earth very badly or unexpectedly. We don't know whether it is good or bad, but we are fear of our survival on this Earth. That's why we are so curious to know what will happen on this Earth. And we want to hear from you what will happen to this atmosphere and what's the predicted climate, all these things from you, from your scientific perspective, sir. And we make a warm welcome to our UL Space Club to deliver your wonderful speech on this very great topic, that's environmental issues and climatic change and all of the technical basis of these kind of interpretations. And we make a very great welcome to this group, sir. We welcome Dr. K. Rajiv, sir, to deliver this wonderful speech. Welcome, sir. Along with that, we are also blessed with several senior scientists from ISRO. V.S. Hegde, sir, is there, and Ganesh Raj, sir, is there, Shashimar, sir, is there, and our PJ Bhatt, sir, is there, and all these are our continuous attenders, and they are supporting us this venture. And we welcome all of you, and again welcome Dr. K. Rajiv to deliver his speech. Welcome, sir.
Thank you, Rajiv. It was very nice and very kind of you. I'm very thankful to you and Kuti sir for inviting me here, and Varun, Sriram, Bharat, all are doing very good coordination. And I have a little bit concerned because the galaxy of senior scientists from ISRO is already sitting. But sir, you should apologize. I mean, you should beg me. I beg your pardon, because my talk will be directed towards the kids, so the young children, and I do not know to what extent I will be able to satisfy your request. So, without spending much time further, I would like to start my talk. Just 1 minute. It is present now. Entire screen. Okay, share. Yeah.
Okay, sir, it's coming. It's coming.
Okay, very good. That's fine. So we will go ahead directly to talk. Is on Earth's environment and its diagnosis from space. As I told you, this is for the young students who are, I know that, I mean, from the kind of interactions that we had, they are really talented people. So I assume some basic physics from them, but that's all. It is not that it is, very high-fi things we will be doing. But at the same time, it will be, I mean, I wish to give you a bird's eye view on what is happening. We cannot cover the entire system, entire topic in a day or maybe in an hour or something like that. But I will attempt in terms of giving you a wider perspective. We know why do we need a satellite remote sensing. We have to observe the Earth atmosphere system. We have to understand our planet and its changes, and securing our environment, benefiting our society. This is the fundamental principles of why satellite remote sensing is required. And this is a very famous photograph, the Earthrise taken from the moon, and you can see how fragile the Earth is and how beautiful it is. You know, if you see the location of Earth that is here, it is around 150 million kilometers from the sun, but is entirely, almost complete energy of the Earth atmosphere system is driven by the sun. Almost, I will say 99.99%. There's only very little that is coming from the geothermal energy. All right. But what is more important is even the food what we took today, actually it is because of the sun. All right. Everything that is happening is because of the sun. And our energy, the way in which it is coming, the way in which we are placed between, from the sun, it's very crucial for the life on Earth as the way in which we are seeing. It's neither too hot nor too cold. What is more important is water can exist in 3 phases. This is a very, very crucial thing, because in the polar region there is little energy that is coming from the sun. In the equatorial region you have large energy that is coming. So all these energy, if it is absorbed in the atmosphere, the tropical region, and it is not transported, it will be a huge problem. And substantial chunk of this energy transport takes place through phase changes in the water vapor. You see, for example, water it get evaporated, takes latent heat of evaporation, takes that energy from the surface, dumps in the atmosphere where the clouds get formed, because clouds are formed by condensation. So that latent heat of evaporation by water is dumped in the atmosphere, transferring the heat, and that is vertically, and also it is getting transported horizontally. You know very well. All right. So this is a very, very important thing, the position of the Earth with respect to the sun. But actually, if Earth was not having greenhouse gases, this mechanism, again, what I am telling would not have been possible, because Earth would have been colder by less than 0 degrees centigrade, less than around 33 degrees centigrade, what we are currently having. I'm talking about a global mean picture. Okay. So that is called the greenhouse effect. So with the greenhouse effect, we are actually able to get all these things. Otherwise, it is not simply because it is placed between the sun, this much distance from the sun, but also because of the greenhouse effect. Okay? Earth's atmosphere, of course, without atmosphere, you cannot inhale oxygen it gives. It's a lifeline. That is, everybody knows. But let me tell you some other things. The Earth's atmosphere and magnetosphere, the magnetic field around it, protects us in several ways. The solar wind, the charged particles, sun is emitting not only the radiation that we are seeing, the sunlight, no, it's also emitting charged particles, protons. They come at very high velocity of the order of, typically around 300 to 400 kilometers per second. It can be even 500, 600. At times it can be in even 1200 kilometers per second. And the number of particles per cc, if you take just at any given instant, it will be of the order of 5 to 10, which is quite high. And at times, sun flare up, and you have the much more impact of the sun coming on the Earth through the charged particles. At the same time, the solar radiation, the way in which we see, is not much affected. But except in certain wavelengths like extreme ultraviolet and X-ray domain, the solar radiation gets increased by orders of magnitude during this, active solar period. And our magnetic field around Earth protects us from all these things, because the kids will know there is something called a Lorentzian force. That is, a charged particle cannot move perpendicular to a magnetic field because it will deflect it. Okay, so it will deflect it in such a way that finally it will be moving along the magnetic field line. All right, so it cannot simply penetrate, not only because of the atmosphere but also because of the magnetic field around it. The second aspect is millions of meteors enter into that atmosphere every day. For example, if you are looking at, sitting at Calicut, at this particular time, in this hour, almost 60 to 100 meteors has come above the Calicut area. But you are not seeing it, you are not facing it either, because they get, decayed in the upper atmosphere itself of the order of 80 to 100 kilometers. Because they come at very high speed, Earth offers a lot of resistance, they get heated up, get ablated, and we are protected. They come with a velocity typically of the order of around 18 to 72 kilometers per second. All right. The third aspect is the harmful radiation, that is X-ray, ultraviolet, the ozone and the way in which it protects us. But not only that, X-rays and extreme ultraviolet is absorbed even above, that is in the ionosphere, and that causes, the ionospheric effects and things like that. We will come to that, right? If you look at the sun is so beautiful, but then, when you look at different wavelength bands, you will see different phases of the sun. Okay, so it is not just the, if you look at the number 5, that is 39%, that is around the blue region, or at 6, that is 6737, that is around the green, bigger pardon, the red region. Sun is looking somewhat okay, but then if you see the ultraviolet region, that is especially in the lower wavelength, X-ray, gamma, and the extreme ultraviolet, it will appear as very, 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 very active. I think it is not the way in which what we see in the other wavelengths, and they affect the atmosphere system. And there is something else called the solar flare, the coronal mass ejections. The coronal mass ejection, there is a massive chunk of material that is coming out of it, and you can see the size of Earth and size of a coronal mass ejection that has taken place. All right. So, if these fellows comes towards us, of course they do come at times. We get protected, but then our satellite systems also should be protected, because some of our satellites are even above the the critical influence of the Earth's magnetic field. So the satellite systems are actually designed for having taking care of these things. And at times when the flare intensity is so high, there are protection mechanisms by which the satellite systems probably temporarily switched off for the majority of the operations, except for the minimal operations. We will not go into those details. All right. So this I already told you. And I told you that the charged particles from the sun can move along the magnetic field, which means they can finally converge at the polar regions where it will travel along the magnetic field and precipitate there, which will in turn lead to aurora, which the kids are very much aware of. And this picture I took today, what is the state of the solar wind right now is what you are seeing here. For one day from 2nd to 3rd October, I want to see only two things. The top one gives the number density of particles per cc, which you may not be able to read the scale, but I will tell you it is of the order of 5 to 6 particles per centimeter cube. And each one of them is traveling with a velocity that is close to, that is the second panel, that is close to 400 to 500 kilometers per second. All right. And we are protected by the Earth because of, from these things. The space weather impact, these kind of space weather impact has enormous effects. We are now talking through communication. The satellite systems can be affected. The weather space, it's called a space weather, okay? It's called a space weather. Solar wind particles coming and interacting with the atmosphere and their changes, all right? You have the position systems that is coming from GPS. GPS systems are now used extensively everywhere, right? From criminology up to, the navigation of, aircraft systems and things like that. And the GPS will be affected. GPS will not be directly affected, but that the values that are given by GPS will be erroneous when you have the changes in solar space weather events because the ionospheric effects and the refractive effects. And unless we correct for that properly, then there will be problem. Actually, there are experts sitting here. I am aware of Subramanian sir and people like that. They worked extensively in this area. And second is the electric power transmission. It is not a problem for us, but then it is a problem for the higher latitude regions, where even the half a city will be just like that. Going out of the light if we are not properly planning. Right? Satellite communications. And why satellite drag? It is not that it is empty there. Okay, satellite will be getting dragged by the atmosphere depending on the number density of particles, as well as the charging and so many other effects. Okay. If you look at the ionosphere, this is called ionosphere. The x-axis shows the concentration of electrons, and y-axis is the altitude. You will find a profile. This is the altitude variation of electron number density in centimeter cube. So at around 150 or 200 kilometer, you will be able to find typically of the order of 10 power 6 to 10 power 7 electrons per centimeter cube. But of course, one good thing is, if you look at the total number of particles, that is the atmospheric molecules, they are much higher. Even at the peak of the ionosphere, they are higher than what is the neutral molecules that are otherwise there. But then this ionosphere has two effects. One, firstly, the ionosphere itself is produced because of the extreme ultraviolet radiation from the sun is getting absorbed, so they protect us again. Second aspect is, there is a critical component in communication that is coming from here. Again, we will not go much into the details because we have to cover quite a bit, right? I already told you that the ionosphere, the effect on the ionosphere by the solar space weather events or even otherwise will be affecting the GPS communication and aircraft navigation because they are actually measured. The basic technology itself is such that they are taking multi-path observations, and if the ray is refracted in the atmosphere, it is refracted indeed, but the extent to which it is refracted has to be purely accurately quantified. Otherwise, there will be it will lead to large errors, and it will be big hazard for aircraft navigation, especially when the aircraft is trying to land or especially landing. All right, and we do have, of course, I do recognize that SPL, my institute as well as other places in ISRO have developed the ionospheric correction system. I am very much aware of the correction system that has been done in our laboratory for ionosphere and atmospheric GPS signals. Now let us come to the neutral atmosphere. The neutral atmosphere, very well that it is nitrogen and oxygen. You see almost they constitute 78% and 21%. But what is more important is the minor constituents like water vapor, carbon dioxide, ozone, chlorofluorocarbons. They are catastrophic. Aerosols and things like that. All right. So let us know a little bit during our course of our lecture. Probably we may a little bit focus more on these minor species, some of them. All right. Especially carbon dioxide and ozone. Just for curiosity, let me tell you, each one of you is carrying almost 400 kilograms of air above your head. Okay, it is a very simple calculation the kids can do. It is the total, the pressure that you are facing now is, we call that as 1000 hectopascal. To be precise, 1013 hectopascal is the pressure. And pressure, you know that it is mass, force per unit area, that is Newton per meter square. I just take, 10 power 5 Newton per meter square. And for this much pressure, you should have almost 10,200 kilogram of air in 1 meter square. I assume the average length and breadth as 0.20 centimeter. So 20 centimeter by 20 centimeter is 0.04 meter square. Multiply by that, almost 400 kilogram, and it will crumble you. But you are not crumbling because there is something else called hydrostatic balance. That is, all the molecules, everything, each one of us, the coconut, the trees, the stones, you and me, everybody want to come to the minimum potential energy. That is, what is possible is at the surface. We still want to go interior, but of course, at least up to the surface. But there is another thing for fluids. For fluids, every fluid want to go from a high pressure to a low pressure. So the low pressure is in the upper region, high pressure is here. But gravity pulls it down. Now you have two forces. One is the gravitational force, which acts it downwards, and the pressure gradient force. That is, it want to go from a high pressure to a low pressure, acting opposite. These two things will balance. So actually, you are not having the burden of carrying, the 408 kilogram of air, but it is there above you. Okay. The second aspect is the thermal structure of the atmosphere. You have a temperature decreasing with height. This is called a troposphere. Its altitude, tropopause altitude, is of the order of 17 kilometers, above which temperature increases. That is called stratosphere. The stratosphere, you have, the ozone. The ozone is the mechanism by which the temperature increases here, because ozone will absorb the extreme ultraviolet radiation, increase its energy level. Of course, then it will be transferred to the atmosphere, giving rise to an increasing temperature. There is a small problem. Very interesting thing again here. The stratosphere acts actually as a lid for convection. All the weather systems that take place, they can travel only up to maximum tropopause, above which this atmosphere is very stable. It will not allow any penetration of the deep convective air that is going up. Of course, there will be leakage of air, that is called the troposphere-stratosphere interaction. But the large scale convection stops either well before tropopause, or it can extend the maximum up to tropopause. Suppose the tropopause was very high, you can imagine what would have happened. It would not have been raining the way in which we want the rain today, but rather there will be large scale, big ice blocks would have been formed whenever there is such a precipitation and things like that. So nature has done so many things for us, the way in which we live. But only thing is, now we are disturbing that we will come to later. All right. The second aspect is the top curve here. That is the solar radiation that is coming from Earth. The red curve shows the total solar radiation that is reaching at the top of atmosphere, that is above the atmosphere. All right. The blue one shows what is actually reaching at the surface. So you see the difference between them. This difference between them, I want to see two things. One, what is reaching at the surface is not simply a contour like what is the red line, but rather there are isolated patches. That is actually coming as absorption from water vapor, oxygen, and ozone and things like that. But there is another beautiful thing that you can see here. You see at around 0.5 micrometer, this is 0.5, okay? And that is a place where the solar radiation is maximum, energy is maximum. That's why that the sunlight, what we call, the sunlight is, what is the color? Yellowish kind of thing. It is actually because the solar radiation peaks at this particular wavelength. All right. But second, there is another thing happening. You see the red curve and see the blue curve top contour. You'll find that there is a big difference between them at around 0.5 and things like that. But as you move at higher wavelengths, that decreases. That difference decreases. Actually, this is because this blue is sky. I mean, the sky is blue in color because this radiation is extinct, because they get scattered out. They don't reach much at the. They do reach, but what I'm saying is the difference between what is reaching at the top and what is reaching at the ground is significantly, considerably lesser. And this difference decreases as wavelength increases, because Rayleigh scattering cross section is 1 by lambda power 4, proportional to 1 by lambda power 4, where lambda is the wavelength. The kids are knowing this. Now you have, as lambda increases, 1 by lambda power 4 decreases, and then you have this difference coming. All right. Essentially, what does it mean is, it is the blue of the sky can be explained from here. All right. We are receiving from the sun, yes, but we are also emitting. We are emitting back. And you can see the right curve here. The left one is what I have just shown you. The right curve is what Earth is emitting. and the solid line that is actually varying, that is the one which is actually emitting from the Earth and seeing at the top of atmosphere. That is if you go above the atmosphere. See what is happening? And before this, let me tell you one thing. I forgot to tell that. If you see the red line here, it is, you know black body radiation. Any body, you and me and the sun and the earth emit radiation. The amount of radiation that you are emitting totally is sigma T power 4, you know very well. But the wavelength variation of the emission, that is the spectra of the emission, will be different for different temperatures. For sun, the temperature is close to 6000 Kelvin. When I say 6000 Kelvin, it is only the photospheric temperature what you are seeing. Interior of the sun has millions of temperatures, but you will never see that because sun is a perfect black body. The layers of the sun is a perfect black body. So here what you are seeing, the curve is actually showing the variation with the wavelength corresponding to, we call the so-called Planck's distribution curve, which means a body at a given temperature T, how it will be emitting as a function of wavelength. All right. So at the temperature close to around 6000 or 5700 degree Kelvin, the maximum comes at around 0.55 or something like that. But you will see for the Earth, the temperature is around 300 Kelvin, close to around maybe say around 28, 30 degrees centigrade. Now you see here, this is what the curve showing for different, temperatures. Okay. Now, but what Earth has emitted is like the solid curves. But what it has reached at the top is only this much. You see, there is a significant decrease in the in the energy that is reaching the top of atmosphere. This is because the greenhouse gases absorb the radiation and re-emit back, reducing the amount of energy that leading to trapping of the energy in the Earth atmosphere system, which warms the atmosphere. Earth's atmosphere. This is called the greenhouse. Okay. You just imagine if carbon dioxide was not present. This would not have been there, the energy would have gone back to space, and the energy that is available to you would have been much lesser, and Earth would have been cooler. Alright? And let me also tell you one more thing. If you increase the carbon dioxide, actually you are increasing this absorption and more trapping of the energy, and you are going to cause a warming. Right? And that's what is happening. And this is the greenhouse effect I already explained. So the energy that is emitted by the Earth is partially absorbed in the atmosphere by the greenhouse gases. They re-emit back, so that the net energy that is reaching the Earth increases, and that is called the greenhouse effect. The most important greenhouse gases are carbon dioxide, water vapor, and ozone. The impact of greenhouse effect in the Earth's atmosphere is around 33 degrees centigrade. If greenhouse effect was not there, Earth would have been cooler by almost 33 degrees centigrade. All right. I wish I could spend enough time here, but this is a little bit complex thing. I may not be able to spend much time here because of the lack of time. I just want to impress upon you only one thing. You just assume that the amount of energy coming from the sun is 100 units. Then the amount of energy that is reflected is 30 units. The amount of energy that is emitted back to the Earth is 70 units. So 100 has come in, 30 was reflected back, and 70 was emitted back. Energy is balanced. 100 unit, 30 plus 70 became 100. Top of atmosphere, well balanced. But if you come to the surface or the atmosphere, this is not so. If you add up these numbers, you will find that there is almost around 29 units in this 100. Around 29 units is excess here, and around 29 units is deficit in the atmosphere. Means atmosphere has emitted more than what it received, but Earth has emitted less than what it has received, net energy. And now this energy is to be transferred. This energy is transferred not through radiation, but it is transferred through something called sensible heat flux and latent heat flux. It is very simple. Latent heat flux means your water vapor get evaporated and taken the energy from the surface and dumps in the atmosphere where clouds are formed. Do you see? That is the number 24. 24 units goes like that. And there is another thing called sensible heat flux, which means you have a hot body and a cold body and you have convection. All right. Essentially, what I am trying to tell you is there is an imbalance between the energy balance in the atmosphere and that at the surface. This difference between them causes the weather. If that was balanced, there would not have been any weather, any clouds, and it will be very difficult. Okay. So the nature by itself programmed so many things. Now, let me tell you one thing. All these numbers are the final ones which are adding up, and they are contributed by greenhouse gases. deep, reflectivity of the surface and things like that. Now what we are doing, we are changing the reflectivity of Earth. We are increasing the amount of carbon dioxide. We are increasing, so many other effects, and we are perturbing the ozone, for example. The net result is you are changing these numbers. You and me are changing these numbers. Means the net equilibrium for the climate is changing, and we are going to a new equilibrium, and that is what is climate change. Okay. And as I told you, you have maximum energy that is coming at the tropics. It has to be transported to the polar regions. So it will be, while it is transported, you have the 3-cell circulation. I will not go into the details of this. I only want to know that there is some circulation cells in the atmosphere. Probably you may be already aware. Hartley cell, Ferrel cell, and polar cell. And the deepest cell exists at the tropics. Okay. And the atmosphere is in motion. This is a stitch of several, satellite imageries in the water vapor band. Just to stitch them together for a few hours, you will get these kind of things. And what I want to tell you, not for a few hours, for a few days. And what I'm trying to tell you is just focus on one thing. A small, tiny, turbine kind of thing going. It's actually the cyclones. All right. So how small a cyclone is with the vis-a-vis Earth, but then what is the kind of impact that it produces? As I told you, we are changing the climate. We are perturbing the climate. But then are only anthropogenic activities? No. Actually, there is a natural process by which climate is changing. And there is an anthropogenic process. The natural process is, Earth is moving around the sun in an elliptical orbit, but its eccentricity, that is the sun's distance, will vary over the course of a year, of the order of 1 lakh years. The sun-Earth distance changes over a periodicity of 1 lakh years. It's called eccentricity. Second, Earth is tilted by 23.5, but actually it is not 23.5. It changes between 21.5 and 24.5 over a period of 41,000 years. And there is another thing, 23.5 with respect to the a normal can be in any direction. That itself can precess. That precesses with a periodicity of 24,000 years. What I'm trying to tell you is, naturally, this is called a Milankovitch cycles. Naturally itself, the Earth, its climate is changing because the Earth's orbital periods are better, but the periodicity of that is of the order of 1 lakh years, 41,000 years, and 24,000 years. But anthropogenic is different. Okay. You see this? This is the observatory from Mount Lava. That's in the Hawaii. You have the change in carbon dioxide. You see, around 1960, it was close to around 305, and today's value. This is the latest, that is 1st October value, is close to 410. This is what is done by each one of us, and we are responsible for this, and we are perturbing the climate. Is that simply, keep on increasing in the past? Fact is no. You just see what is the year here. X-axis shows the year. 1750, 1800, 1850, 1900, up to 2000, and 2020. You see, this increase is only after around probably very fast increase is after 1950. And a slow increase after 1850. But before that, it was rather not that much changing. Let us still go back in time. You see this? This is in thousands of years. The total scale is 8 lakh years. Okay, x-axis is 8 lakh years, and the 0 indicates current, that is today. Okay, you will see that there is a rapid variation in climate change. There is a rapid variation in increase in carbon dioxide. In the the thousands of years before, it was close to around 260, 270. Today, the value has come to 400. This is our contribution to the climate, and we are going to face it. Okay. If you see the carbon dioxide level variations, even beyond that level, you will find that, again, the same scenario. Okay. Now, what to do? Since you are perturbed, yes, now what to do? There are 2 scenarios I will show you. This is taken from the literature. All these things, what I am talking is standard literature. Okay. Incidentally, the increase in carbon dioxide, it is called the Keeling curve. Okay. The kids should know that. All right. Now, suppose you are stopping all the emission of carbon dioxide suddenly today. That is what is shown by the vertical line and the upper graph. You are bringing it down, but still the carbon dioxide amount in the atmosphere will continue to be 410 or so, because carbon dioxide lifetime is very high, of the order of several decades, more than 30, 40 years. So even if you stop carbon dioxide production today, I will not say stop, but at least much reduce the emission. you are still going to continue with this. But that is if you are doing it today. And we know that you cannot do it today because carbon dioxide emission come from the anthropogenic activities. All the anthropogenic activities cannot be stopped. The industries cannot be stopped. The work will suffer. The industry, the economy will suffer. And we cannot simply stop it. Okay. So there's a second scenario which is put up. That is, you continue to emit for some more time and then come to a plateau. This is the second worst case. The carbon dioxide amount will keep on increasing up to around 700, even by the end of 2100. Now you are between these two scenarios. We do not know what is really going to happen. It depends on you and me and the nations. The nations are coming together to have proper emission trading mechanisms and things like that. I mean, control of the emission of carbon dioxide. That anyway, that is part of the climate change negotiations and economics of climate change. The second aspect that is affecting the climate is aerosols. You know that aerosols, that is the tiny suspended particles in the air. Okay, the suspended particles in the air, when they are small in number, they should be there. Actually, without aerosols, clouds cannot form. Clouds can form, but then it will be homogeneous condensation, and the type of cloud what you are going to get will be completely different from what you are getting today. But if the aerosol amount is increasing like anything, it becomes a curse. Okay, and that we are facing. It affects our health, and what is more important is it affects the environment. In a sense, people may say one way is, when aerosols are there, the amount of radiation reaching the surface will decrease. It's called the direct effect of aerosols. Means it is good. It will reduce the amount of radiation that is reaching the surface. It will cool. But the fact is, aerosol lifetime is of the order of 7 days. If you stop the aerosol production today, in another week or 10 days, the background aerosol system will come down. This happened during the COVID time. And unfortunately, I was not having an image of that. But let me tell you, during the COVID time, when the activities were shut down, the northern belt of India, where Indo-Gangetic Plain is one of the most polluted regions in India. Okay, so that region, the pollution level came down like anything. And your carbon dioxide changes will not be balanced by the kind of aerosol changes. All right. And also, there is another type of aerosol. You see, this picture itself looks hazy, brownish kind of thing. It is because you have black soot aerosols mixed with that. All right, or some other organic aerosols. Okay. The result is there will be large absorption, and absorption will cause heating primarily in the atmosphere, which will change the atmospheric conditions. There are a lot of natural processes by which the aerosols are produced. We cannot control them, like volcanic eruptions or desert dust or sea salt, forest fires and things like that. Sometimes it happens, but there are anthropogenic sources like biomass burning, industrial emissions, oil fires, transport. The vehicles that you are producing, why the burning that you produce, for example, in your backyard, you may be burning something. All these things also produces aerosols. And the global distribution of aerosols, if you see from the space, it is the way in which it is looking like this. You see, this is the whole globe, it is over the ocean. You see, the red region shows very large amount of aerosols. And that is primarily coming from the dust. This is near from Sahara in December, January, February. But look at June, July, August. This is Indian region, the Arabian Sea is thickly, polluted because the dust, but that dust coming from the West Asian desert region. This is natural, but superposed on that, we also produce the anthropogenic things. We can delineate the effect of these two. This is an expert field. I am not going into the details again. The third aspect coming to is ozone. We know that ozone is protecting life on Earth because it absorbs the extreme ultraviolet and ultraviolet radiation. Let me tell you one thing because the kids are there. You see, the ozone is measured in Dobson unit. I'm not going to explain to you in detail about Dobson unit, but you just take it like this. 300 Dobson unit is the average amount of ozone in the atmosphere. This is for the entire column. And that means if all the ozone molecules in the atmosphere vertically up, in the stratosphere is brought down to the Earth's surface, at the Earth's surface pressure, the thickness of that ozone layer will be only 3 millimeters. You understood what I'm saying? So 300 Dobson unit correspond to 3 millimeters of atmosphere. That's why just the line above, I'm writing as 0.01 milli-atmosphere centimeter. I'm not going to the details of this due to lack of time, but I want you to understand this. Dobson unit is the column, ozone concentration. Column means total atmospheric column, okay, vertically up. And the average value is around 300 Dobson unit. It varies with the latitude, it varies with the time, but average is close to that. And that means around 3 millimeters of atmosphere. If you bring down all the ozone molecules to the surface, they are not at the surface, they are in the stratosphere. But if you bring up all of them to the surface, the thickness of the ozone layer will be 3 millimeters. And you just imagine that 3 millimeter is the one which protects you and me, the way in which life exists today. And we know that we are again disturbing them because chlorofluorocarbons we are emitting, and chlorofluorocarbons are supposed to be wonder gases. They are completely, they are non-reactive when they are here. But when they go up in the atmosphere, the solar ultraviolet radiation, releases chlorine from that. That chlorine will react with the ozone. This is the equation that bottom panel shows. Chlorine will react with ozone to form ClO plus O2, and that ClO will again react with O3, ozone, to form Cl plus O2. If you sum up this reaction, where is chlorine? There is no chlorine. It is 2O3 became 3O2, and chlorine goes back to the atmosphere. It is like a catalyst. All right. One chlorine atom can destroy of the order of 10,000 to 1 lakh ozone molecules before that is removed from the atmosphere. And this is what is the the ozone hole. And ozone hole will not appear every time. Let me also tell you, ozone hole appear. In the current scenario, I am telling, the ozone hole appear mainly in the Antarctic region. And in the Antarctic region, ozone hole means there is nothing called a hole. But actually, the column ozone, which I was telling 300 Dobson unit, the amount will come down below 220 Dobson unit. Then we call it as ozone hole. Okay. So you can see the graph that is shown on the right side. There's a pink hole kind of thing where the Dobson unit is less than around 150 or something like that. That is actually ozone hole. That is in the Antarctic region, and it occurs only in the just after winter and the early spring, because the chlorine is to be liberated from the atmosphere, for which radiation is required, solar radiation. All right. So that's why it is in the spring. And second, there is one more reason. The ozone cannot be simply destroyed like that. You need a surface area. That surface area is polar stratospheric clouds. And the polar stratospheric clouds disappear when the solar radiation comes, but they are available in winter. But in winter, there is no radiation that is coming in, so chlorine cannot be liberated. So you see, it's a combination of all these three things together. You have the polar stratospheric clouds, you have the first rays of the sun coming, releasing carbon chlorine, destroying ozone, explosive growth, destruction, and it will be rapidly falling to a value below this. And there is another third reason. There is actually, we are producing, the equatorial region, the tropical region is producing maximum ozone. And it is transported to the higher latitudes through a circulation called the Brewer-Dobson circulation. But it is not able to enter into this region because there is another natural effect that is called the circumpolar vortex. There is an intense current system that is going around the pole, which prevents the tropical air to enter into the polar region. So that also is a cause for this. Okay. Now we should also be thankful to people whom you may never know. Okay, there are three people: Paul Crutzen, Marino Molina, and Sherwood. Mario Molina and Sherwood Rowland, who were awarded Nobel Prize for the prediction that ozone hole will occur, ozone destruction will occur. And you should also be aware that when you are simply telling an academic research like this, it is not so, because there is huge amount of resistance that will come from the industry. Because if the result is false, then there is huge amount of economic loss, which is unaffordable. All right. So they fought against all these things, and they were finally awarded Nobel Prize for this thing. And then you have the 1987 Montreal Protocol, where all the several countries in the world came together and said, no, we have to stop it. So the chlorofluorocarbons were slowly, disappeared. And it doesn't mean that the everything has come back to the normal. Ozone hole development, further enhancement has stopped. That's all. It is not that the ozone hole is now fully filled. Next September also it will be there. I will show you a movie later on when I get time, probably at the end of the talk, because I want to tell you something more. All right. So now the comes, you have two scenarios. One is, suppose you are not implementing Montreal Protocol and you are implementing Montreal Protocol. The left side is, what if you are implementing Montreal Protocol? The right figure shows, what if you are not implementing Montreal Protocol? And you see the whole of the Earth will be having ozone around 100, less than 120 or 100 by 2064. Many of you will be young, senior level citizens at that time, but then you will have your kids, you have next generations coming up. None of them can survive. And if you see, because you are implementing, this left side will be the scenario. Okay. So this is September 2020 ozone hole. It appeared over the Antarctic region, and this is what it is. The future. There's something called IPCC. You can go and Google on IPCC, Intergovernmental Panel for Climate Change. There are this IPCC also received Nobel Prize for of course for peace, because of the kind of protection that they are doing for the earth. All right. IPCC is an intergovernmental panel for climate change. They periodically review what is happening and make assessment reports. There are representatives from India too, and they are giving here two scenarios. One, I'm not going into what is RCP 2.6 and RCP 8.5. They are sort of two extreme scenarios. The temperature in 2080 to 2100, that is next 100 years, how much the temperature is going to change is what is shown here in the top panel. And it is all red. Red means temperature can increase even by of the order of 6 to 7 degrees centigrade if you don't implement control measures. Okay. But if you implement control measures, still it is going to warm. It may be warming of the order of 1.5 to 2 if it is very strict. The second thing is the bottom panel shows what will be happening to the precipitation. So there will be decrease in precipitation or increase in precipitation. But what is happening is the right side shows that there will be increase in precipitation. We may be happy, but that precipitation will be through extreme weather events. It will not be just the kind of precipitation that we were receiving earlier, but the extreme weather events will increase. Okay, which is also not good. The second thing is the global average temperature in a realistic sense will be between these two. By 2100, the temperature will increase by around 1.5 to around 4 degrees centigrade. That is the assessment. Depending on what is the kind of control measures that we do. What is more important, the sea level also will rise between around 40 centimeter to around 80 centimeter, 70 to 80 centimeter. By sea level will rise, again depending on what is the kind of control measures that we are going to implement. Right? For making all these things, you need observations. Okay. The observations from in situ measurements, that in situ means at a given place. For example, if you are making a temperature measurement in your house, it is in situ measurement of temperature. But if you want to get a global picture, you require a satellite system. So we need highly accurate systems for reliable and systematic monitoring of the Earth atmosphere globally. We also need them for natural resource mapping, agriculture safety, food security, so many things. So what are the application areas? The resource management, for example, forests, minerals, water, fishing, agriculture crop monitoring, crop yield forecast, meteorology, daily weather forecasting, cyclones, the tracking and landfall, disaster management, urban planning, pollution monitoring and emission trading, climate change monitoring, national security, navigation means aircraft navigation included, satellite safety, and the list is endless. You have a host of applications that come from space things. Space-based observations. And basics of remote sensing tells that, you are hearing me, but that is acoustic wave. But unless you are making an in situ observation, in satellite also you can have in situ observation, but for certain species like in the ionosphere, charged particles and things like that, or the electric field. But then, if you are observing the Earth for water and things like that, it has to be through the radiation that is reaching the sun. That is the electromagnetic radiation. You detect certain electromagnetic radiation. Which wavelength the band, it will be deciding on what is the kind of application that you want to have. I'm giving you a simple example. If you want to detect clouds, one is you can detect what is the reflected amount of radiation. That is the reflected visible band. The wavelength of the band required is around 400 to 700. But suppose I will show you in the next slide. In the night time there is sun. So in the night you cannot detect clouds. You can, provided you are actually detecting in the terrestrial IR that is close to around 10.5 micrometer. And in addition to water, the visible radiation, the IR observation will also give you the brightness temperature, and that will give you an indication about what altitude is the height, cloud height. That means whether it is a deep convective cloud or a shallow cloud. All right. The electromagnetic spectrum, I assume that you know this. I am not going into the details because of lack of time, but let me stress upon this. The top graph shows what I explained to you in the beginning, the Planck's distribution curve. That is the amount of energy emitted by a black body. The y-axis is how much is the energy emitted, watt per meter square per micrometer. X-axis is the wavelength. And you see what is the top curve is for 6000 Kelvin, that is close to the sun. And you see 300 Kelvin, that is for Earth. You will find that most of the radiation that is emitted is in 10 micrometer. Close to. Of course, it changes from, it varies from around 3.5 to around 50 micrometer. All right. The bottom graph shows what is the effect of atmosphere. See, your intention is to see the surface or see the atmospheric effect. Okay. That means the transmittance of the atmosphere has to be fairly high. So in the visible band, what is y-axis shows what is the transmittance, means the amount of attenuation that will be taking place because of the atmosphere. So 1 means it will not be attenuated, 0 means it will be completely attenuated. Okay. So in the visible band, the attenuation is rather small. But if you come to the infrared, 10 micrometer, there is large amount of, close to 10 micrometer, there is large amount of attenuation. But there is one band close to around 10 micrometer or 10 to 12, which is having high transmittance, 0.8. That's why for detecting sea surface temperature, clouds and things like that, we observe in around 10 to 12 micrometer. Of course, if you want to detect another type of cloud, you may require at 6.3 micrometer, which I am not going into the details again, okay, because of lack of time. And what is, I mean, there are several configurations of the detectors, several configurations of observations. I'm giving you one example of a push broom scanning using a CCD array. I want to stress upon 3 things here. One, the satellite as it goes, it just looks, you see along the line that is seen here, this is called the scan line. And a scan line comprises of several, small pixels. Okay, so that is a pixel. That is the minimum detectable area by a particular sensor. Okay, it cannot have smaller area than that. All right, in the next graph I'll explain it further. So several pixels together in a line constitute a scan line, and the total width of that is called the swath. These 3 are technical terms that are used in remote sensing: pixel, scan line, and swath. That you should keep in mind. Okay, in the next line it is shown what is resolution. So pixel resolution, satellite is here. There's a field of view. You can actually see the field of view by this much degrees. It will come. Extend an area of this much here. Actually, it is something like r theta. If r is the radius and theta is the angle, r theta is the arc length. Similarly, so that is the pixel resolution. And because of the curvature of Earth, at the nadir you will have, nadir means down looking. You will have one resolution. When you go to the edge, you will have another type of resolution. All right. And the reflected, this is another important property that is being used in satellite remote sensing. The reflectance of various ingredients of Earth are different. For example, clear water, that is what is shown here. The reflectance at different wavelengths are different. The grass, that is a solid line. Okay, the black solid line. The concrete means if you observe at different wavelengths, you will get different reflectivities. We also know that the reflectivities are different for different kind of surface compositions, like water, grass, concrete, sand, or agriculture field and things like that. This is one of the most crucial things that is being used for satellite remote sensing of either surface and at the same time at the atmosphere also. All right. The advantage of satellite remote sensing is it can cover a large area by the same instrument. That means same calibration. You don't have to have several instruments having its own calibrations. Then truly representing a region, unlike a point observation. If I make a point observation at Trivandrum, I will say a Palayam area, it will not be necessarily representing Trivandrum even. All right. And they are not biased by local conditions and instrumental variations. But there are several disadvantages for satellite observing systems. One is they are not direct observations of the parameter. They are inferred. Actually, from the radiance that you get, the electromagnetic radiance that you are getting, you are inferring what is the kind of property, which will have several assumptions. We call that an inversion. Okay, they assume several parameters, so it need not be necessarily accurate. 2, it can be accurate provided you have good knowledge about the system and good radiation transfer computations. I'm not going into the details; they are on the hi-fi lines. You don't worry about them. But then you also know that it is not the direct observations, but then indirect observations through remote sensing. Okay, so it will have its own limitations. Then depending on the spectral band, some parameter may not be observable at all. For example, when you have clouds, you cannot observe the surface in visible band or thermal infrared. Okay. The best strategy is to have together satellite measurements together with the ground-based observations. Ground-based observations you cannot extend very widely over the entire globe. There are places where you cannot go also. There are satellite observations, and even over the places where in-situ observations exist, you should have satellite observations, and that satellite observations will be inverted based on what is the information obtained from the in-situ observations, and the in-situ observations will be used to validate the satellite observations. So you should have a mixture of them. Okay. The examples of the satellite remote sensing, I will take probably another 5-6 minutes, maybe around 7-8 minutes. The examples, you have the polar orbiting satellites, you have polar sun synchronous satellites, you have geostationary satellites, you have low inclination orbits. This you know, a satellite is going around the Earth because Earth is pulling it down, but the centrifugal force, mv square by r, you know it very well, is balanced by gravity, that is gmm by r square. So it is something like the earlier scenario which we are telling, pressure gradient force balances Coriolis force, okay? So the gravitational force balances the centrifugal force, and the velocity is in this velocity vector in this direction, it will keep on orbiting. So at a particular orbit, there is a particular orbit means the particular radius of the orbit, there is a particular velocity, all right? This also explains incidentally why there is weightlessness in orbiting space station, okay? Because it is balanced. The gravitational force is balanced by centrifugal force, so you will experience weightlessness. It is not that Earth is not attracting. There is a misconception that in space there is no weight. It is not so. There is weight. Earth is absorbing. I mean, you know, attracting. You will have the weight, but that weight is counterbalanced by the centrifugal force. This is a pictorial representation of what is polar orbit and what is geostationary orbit. Geostationary orbit will be usually in the, not usually, it will be in the equatorial plane, and the polar orbit will be, the satellite will be going north pole, south pole, that kind of thing, with a small inclination. All right. While it is going to the north-south, it will be observing an area. This is what I told you earlier, swath, that the x direction, the horizon, I mean, shows the width of the white patch is the swath. And as it goes, it keep on observing that particular belt. And it will come back. After around, say, 102 minutes, it will come back to polar orbiting satellite. But while coming back, Earth has rotated. So Earth will be showing a different region. For example, earlier, this is a typical example, United States. It was through the one coast of, east coast of United States. When the next orbit comes, it will be passing through the central to west coast of United States. This happens. So different orbits, when you compile together in a day, you will be getting the total picture of the Earth. One thing which you should know, the orbital velocity of typical orbital velocity. This is typical, I told you, it's at 800 kilometers, it will be close to 7.4 kilometers per second. And the orbital period is of the order of 102 minutes. And just imagine, you have the International Space Station. There are people there. For them, one day, that is one sunrise and one sunset and back to one sunrise, is around 102 minutes or 100 minutes, or maybe in the space station it is close to 92 because its altitude is slightly lower. So in around 92 minutes, the astronaut faces one sunrise, one sunset, and back to the sunrise. All right. This is the geostationary orbit, where the orbit is along the equatorial plane. For the geostationary means it will be stationary with respect to a location on Earth. I want to inform the kids. It is not stationary. It is orbiting, but orbiting at the same rotation speed as Earth. So that if you look from one particular place, for example, if you place a satellite above India, the satellite will rotate at the same rotation speed as Earth. So that when India is rotating in one, Earth is rotating in one day, it will follow that. So that the satellite will appear as though it is. It will appear as though for us that the satellite is stationary. That's what it is called, the geostationary. There are several advantages. You can keep on observing one particular location throughout, but then from that one geostationary satellite, you cannot have the whole observation of the Earth, unlike the earlier polar orbiting satellite. ISRO has state-of-the-art facilities for space and atmospheric research. Political boundaries become weaker in space and atmospheric research, and India is presently a world leader, you know very well, in the tropical, lower, middle, and upper atmosphere and ionosphere magnetosphere. And this is the story of INSAT, from INSAT 1, INSAT 1B, INSAT 2, Kalpana, INSAT 3A, INSAT 3D, 3DR. We have state-of-the-art systems. Time evolution, right from something like 1982 until now, there is an evolving thing as far as INSATs are concerned. We also have several other satellites in between. IRS satellite, IRS-1C, IRS-1D, they are for remote sensing. And also we have atmospheric research satellites like Megatropics. We also have the Saral, Altica kind of thing. And in future, we are going to have GA series, which is very high resolution systems, INSAT 3DS, and all these things are available in the public literature for you. Okay. And what is INSAT having? INSAT is having, in addition, of course, INSAT in India there is one uniqueness. INSAT has communication payloads and the remote sensing payloads. I'm only talking to you about the remote sensing payloads. The passive remote sensing is the tech. Passive means you just look outside. what you are seeing is passive remote sensing, because solar radiation comes, reflects, and then your eye receives it. That's called a passive remote sensing. Or you, in the night time, if you send a torchlight, the torchlight reflects back. That's not passive. Actually, you send a radiation, you are getting back your radiation, reflection. That is active. So what VHRR does is, it doesn't send anything, it only receives. It's like something like our eye. Our eye doesn't send anything, our eye only receives. That's passive remote sensing. There's something called the VHRR, that is very high resolution radiometer. Generally, it observes in the visible, infrared, and water vapor area. And in such series, you know very well, Kalpana 1 is another. And we also have state-of-the-art systems now that is much more, generation after, that is INSAT 3D and 3DR, which contains imager as well as the sounder, which is, you can actually probe the altitude profiles of temperature and humidity from this. All right. This I want to explain to you. This I took yesterday data. You see that this graph is what INSAT 3D has viewed the Earth yesterday, that is 2nd October, in the visible band at different times. Midnight, the top left is midnight, 1:30 in the midnight. We all were sleeping because it is dark. But in the, in the western, the eastern horizon, you can see the light that is coming from the sun, just as an arc. This is at 6 o'clock in the morning. So the sun is probably over somewhere in the Pacific, but you are getting the first early night, and the African side is still dark. And in the evening, 1800, you have the sun that has passed us, and now it is over the African or European region, and the the Pacific and areas like that, or East Asia, is dark. And at noon time, you see, this is the scenario. We are full blown. So you have to come from the top left to top right to bottom right to bottom left. This is for a day, as you see from the satellite. Now the disadvantage is nighttime. What is happening, you will not know if you are only observing in the visible. But we have a method. That is the beg your pardon for this. The writing. I'm very sorry. It's actually it is not visible band. It is infrared. 10 micrometer, 10.5 micrometer. Okay. You please note down. It's not visible band. It is 10.5 micrometer. That is infrared band. But infrared, you see, 1 o'clock you can observe, 6 o'clock you can observe, 12 o'clock you can observe, 1800 you can observe. I'm now just going back and forth. Okay. This is visible, and this is infrared. So with infrared, you can have throughout the day, and that is what is the main application, one of the main applications of infrared observations. We also have mechatropics. Since the time is running short, I will not go much into the details of this. This is purely for atmospheric research. This is an Indo-French mission, and this has made state-of-the-art findings. This has state-of-the-art instruments on board, and there are several. There are 3 payloads, actually 4 payloads. One of the thing is Karab. I will not go much into the details. Just to tell you that we have systems for atmospheric research, we have meteorological research, we have space research. Just to impress upon you a total view. Okay. This is the net radiative effect of the clouds that is derived from the mechatropics data. Again, I will not go into the details. This is coming as Shajil sir was telling, ISRO story of the week, published. You can go to ISRO website. We also have the active remote sensing techniques, which I told you. I am giving you one example, is SCATSAT, which is you send a radiation, electromagnetic radiation that is in the radar. The frequency is 13.515 gigahertz. You send it, you receive back what is a scattered signal. Your pixel resolution, which I told you earlier, is 25 kilometer by 25 kilometer here. The total swath is close to 140 kilometer. Beg your pardon, 1400 kilometer. It is not 140, 10 I missed. I am very sorry. It's 1400 kilometer. And these details you can get from, there is, ISRO has a website. It's called the MOSDAC. Okay, mosdac.gov.in. Visit ISRO's Earth Observation Data Portal. You will get all these information. Okay, and the data is free. This is the high resolution observations. If I zoom in, you will get very fine observations of the winds from there. Okay. This is essential. You see, these observations were being carried out over the ocean, where you don't have otherwise no data, except probably ship observations for wind. And the scatterometer plays a very, very important role, including the genesis of a cyclone. The moment a cyclonic vortex has started generating, this fellow can detect it. Okay. This can also observe the polar regions. I will skip it. Just 2-3 slides I will be running through just to show you what are the other things which we can have. This is the night light that is detected by the satellite. Okay. stitched by several satellite observations stitched together. You can, we may think that what is so great about it? It has several applications, actually including spying, because what is the development that is taking place in each region can be monitored by somebody else based on the light which is shown is an indicator of the development, if you want to call that way. And in fact, it is indeed. And the cities and things like that will be much more brighter. And you can see the Africa, okay, the Sahara, the other southern Africa, and even the Brazil, the Amazon region. Why even Australia, Central Australia, and things like that, except in the brims, okay, and the Himalaya, the Gobi Desert. You can see the polar regions, right? There, those regions are not having light, means the activity is less, right? And this is for India specifically. You can see the development that is taking place, and I will show you the next one. This is interesting. This is taken from the International Space Station, and you will see a red line that is going here. Actually, people were, several photographs when people were analyzing, they found it is propagating, but actually it was the the barrier that is generated between the Indian boundary and the Pakistan boundary. Okay. So what I'm trying to tell is there are a lot of applications for satellite remote sensing, which we may not imagine. Forest fires. You can have a global map of the forest fires, which are the areas where forest fire activity is going on. Global lightning. Where are the areas which are having lightning and where it is maximum? So many things you can have from the space observations. Sea surface temperature. Sea surface temperature is one of the very crucial parameters, not only for atmosphere, but even for the fishing zone. The fishes don't like too hot and too cold. There is a temperature, optimum temperature over which they will be present. Okay. So many applications which we may not imagine. Soil moisture, that is amount of moisture content in the soil, which is a crucial parameter for the agriculture. So we have a lot more, and it is not just based on one observation. It is based on a multitude of observations. And if you are talking about India, we have satellite systems in the polar orbit, sun synchronous orbit. We have in the geostationary. We have low inclination satellites. We have aircrafts, instrumented aircrafts for atmospheric observations. We have ships in India where instrumented ships carry out observations of atmosphere and the ocean. We have the ocean buoys. We have the ocean network of observatories. We have glaciers, and we have a land network of observatories for so many things, for aerosols and so many other, even GPS observations and things like that. We compile the data together, and you have a spectrum of area that you are trying to understand, right from the Earth's surface to the atmosphere, to the ionosphere, magnetosphere, to the sun Earth, okay, space weather. And I stop here. I thank you very much for your kind attention. I know that I skipped a little bit. I was a little bit fast, and let me emphasize there were 2 mistakes in my slides. You please note that. I have told you where it was, and thank you very much.
Thank you, Suresh sir, for your wonderful talk. We will say that exactly it's a talk of everything about space and its exploration and use of satellites and remote sensing. And the way you arrange the content, that's wonderful. As a teacher, I am interestingly watching your arrangement. You pack this information in a gradual way, and that included everything. That means you discussed almost everything we have go through in the past 19 webinars. We can say that. And it was also, there was a lot of information the students were continuously asking. Normally, there was a question about the ozone hole in the previous webinar that was answered unattended. And now we got, there is no hole. And even in the September 16th, we celebrated the day of Ozone Day and ozone hole. And now we all understood that it's only a decline in the ozone unit, and that we realized that lots of things are there. And you informed us that the climatic change is not the cause of all are caused by anthropogenic activities, but there are so many natural things are there. But we should be so cautious to maintain the carbon dioxide emission, and we and our next generation want to survive there, and we have to face a little bit difficult life after 2015 if we go like this. And everything you included in this lecture in our channel, YouTube channel. I think the students can go through it again and again. Even as a teacher, I also use it as a reference from this YouTube channel. Your talk, you made a history to this talk, and before we enter to the question and answer session, we want to maintain this tempo and this kind of enthusiasm among our students to ask the question directly you. And I invite Kutisa to make a little comment on these things, and after that we will have the question and answer.
Thanks, Shajil Mash. It is an extremely important day in the activity of Space Club. I am very, very sure that the students have got their rich food in today's talk from Dr. Rajiv. And this is the second time I am listening to Dr. Rajiv. Last year, Dr. Rajiv was here in our planetarium at Calicut, and he had delivered a very, very informative, knowledgeable talk. And from then onwards, I have been thinking how to get him again in Calicut to make our students listen to Dr. Rajiv. That is now fructified today. I am extremely thankful to Dr. Rajiv for doing this very good job. And I also acknowledge my grateful thanks to our Somnath sir, Director VSSE, who has graciously nominated yourself for this job. And that has enabled a great beginning of World Space Week. Tomorrow it is the official beginning, but today's talk itself kickstarts that activity, and we have lined up a few program which already shown there, 5th, 7th by our own ISRO people, and 9th by the students, and 10th we have a talk on melting ice and climate status from space by an oceanography person, and that will be the concluding of the Space Week on program. So I don't want to take much time because there are a lot of anxious students waiting to ask searching questions, and I want to do the forum for them, but I have a duty to express my grateful thanks to Dr. Rajiv for doing a very commendable delivering a very commendable talk today. Thank you very much, Dr. Rajiv. We'll keep meeting. Thank you very much.
Thank you.
Thank you, Kuti sir. And all the world start its Space Week only tomorrow. We start the Space Week celebration today itself by this wonderful talk that is happening there. It's a very wonderful thing, and all the students will follow you, sir, with the information and the thing with you, sir. We felt the treasure of knowledge and experience with you with these few words, and even our Bhatt sir also made a good comment on your talk, excellent one. And after and we don't want to lose the tempo for students, and we just rush into the questions sections. They are eagerly waiting for that. I invite Varun to lead that Q&A. Varun and Sriram to lead that Q&A session.
Sir, thank you for inviting me for the question and answer session. First of all, thank you, Rajiv sir, for a wonderful session. And it was very nice. Like Shajil sir said, it was an introduction to Space Week celebration. Like you said about how satellite technologies are used to these kind of things. So it's really related to the theme of this year's Space Week celebration. So I would like to directly move to the question and answer session. We have few questions here. So we just collected all questions together. So I will ask one by one, sir.
Okay, sure. Good.
So the first question is from Farida. I want Farida for asking the question to directly to him.
Yeah.
Farida, please switch on your mic and you can ask the question to directly to the speaker.
Hi, sir.
Hi.
I am Rifa Fatima from Kozhikode.
Okay.
I am studying in 8th standard in GVHS Sakoli.
Mm-hmm.
I think that one layer protects us, ozone layer protects us from UV rays from sun. But PFC gas causes the depletion of ozone layer. And the ozone hole is seen in the polar region. But with a large amount of CFC gas, why the ozone hole is seen in the polar regions?
Actually, firstly, let me apologize for being very fast. Actually, I got a comment from in the chat that you are very fast. But I wanted to cover a little bit of. I told you, bird's eye view. That's why I couldn't explain in detail to this particular thing. It's a very interesting and important question. The question is, why the polar regions only witness the ozone hole? Yes, Farida, is it not? I understand that the question is why the ozone hole is present only in the Antarctic region. The fact is, naturally itself there is ozone hole. It is not ozone hole, but then ozone depletion. Because ozone is produced maximum in the equatorial region and transported to the polar regions. And when the air wants to enter into, there is something called a circumpolar vortex that is very strong in the winter. Okay, in the winter, the polar region air cannot simply enter. Bigger pardon, equatorial air, tropical air, which is ozone rich, cannot enter into the polar regions. The result is the ozone available there will be keep naturally. To add to that, ozone destruction take place. Ozone will take place because another thing. You are emitting chlorofluorocarbon. This chlorofluorocarbon, when it go up into the atmosphere, what will happen is the chlorine will be liberated from that through reactions. Okay, the liberated chlorine will react with ozone. So Cl plus O3 will become ClO plus O2. That ClO will react with another ozone. ClO plus O3 will become Cl plus 2O2. What will happen is chlorine has come out of the reaction unhurt. This is the basic cause for the ozone hole. Now your question, that is why in the Antarctic region only it is there. The reasons are two. First is, you have to have the chlorine liberated. That happens in the when the sun is available. You also have to have a surface area over which this reaction can take place. That surface area is provided with something called polar stratospheric clouds, PSCs. The polar stratospheric cloud is maximum during winter, and they decay, they disappear by spring and summer. Now you have a combination. First rays of sun comes from the winter, at the end of winter, the beginning of spring. First solar radiation comes. This radiation will liberate chlorine. The chlorine is available. At that time, chlorofluorocarbon, beg your pardon, the polar stratospheric cloud also is available. Chemical reaction can take place, ozone destruction can take place. Subsequently, during the summer, this the polar stratospheric cloud goes up. Chlorine is available, but it cannot be that efficient in producing ozone destruction. Why in Antarctica alone? You have polar stratospheric clouds. The polar stratospheric clouds play a very crucial role in ozone destruction. That's available in the Antarctic region. It doesn't mean that if you continue with these chlorofluorocarbon activities, it will be limited to Antarctica. It will be expanding and it will fill the whole globe as one figure which I showed you. Is it clear to you, Farida?
Yes, sir.
So thank you. Let's move to the next question. It's by Fatima Rusfida. I invite Fatima Rusfida to ask the question.
Yeah, Fatima. Hello. Probably she has muted.
Yes, sir.
You unmute Fatima and then ask the question.
I think she's not in the meeting right now. So can I ask the question directly to you?
Yeah, sure.
So the question is, Is there any remedy other than controlling to protect nature or not to have the effects of climate change?
Okay. So is there any remedy? Correct?
Yes, sir.
It's a very, very important question. There's an area of research that is coming up. It's called geoengineering. Means how to protect the earth, from the climate change. You can propose any wild idea. It may be feasible, it may not be feasible. Just propose and see the viability of that, and then the utilization of it will follow. One typical example is you want to reduce the amount of radiation that is reaching the surface. One way is you put the highly reflecting spheres all around the earth. I'm just putting a wild idea. People have put forward. Okay, it will reflect a part of the radiation that is coming in, reducing the amount of solar radiation available here. It will decrease the amount of heating, so it will partly annul the effect that is produced by carbon dioxide. Is it a viable solution? Is it a real solution? A solution which will not have other implications? Story is different. But people are thinking in this line. There is another example is people are telling, you put a lot of iron in the certain oceanic areas, which will produce a lot of phytoplanktons. And phytoplanktons will decay after some time, and dimethyl sulfide will come out. It will form aerosols, and that will be over the oceanic areas. So aerosols, they are not absorbing aerosols. They are not that bad aerosols. So result is the aerosol amount will increase over these oceanic areas. The amount of radiation that is going back to space will increase. So again, causing a cooling. So third aspect is the planting of trees, and planting of trees in which location? That's again mattering. Okay. So this area of research is called geoengineering. It is indeed possible to regulate one effect, but then when one effect is regulated, the other effects will come up like anything. So the best way is not to disturb the nature. That is the best solution. But if you don't have solutions like that, then there will be other measures that has to be taken. But I don't think that other than the natural way of doing things, I don't think there is any better solution. Natural way means you reduce the amount of CO2. You cannot stop the amount of carbon dioxide production, because industry will produce, even the electricity production will require, So you cannot simply avoid, or vehicles will produce. You cannot simply avoid them. But at the same time, you can have proper emission systems, minimization of things, and avoid critical things like chlorofluorocarbons are avoided now. The halogens that were destructing ozone is now removed. So they are the remedies rather than going for the other geoengineering. It doesn't mean that geoengineering is bad. Geoengineering is good. But what I'm saying is the first solution should be the other one. Understood?
Okay, sir. Thank you, sir. Can I move to the next question? It's very nice that our students ask most relevant question at this situation of Earth, the present situation of our Earth. It's very nice to ask this kind of relevant questions. So can I move to the next question, sir?
Yeah, go ahead, please.
It's asked by Mr. Manjunath. So I invite Manjunath to ask the question directly to our speaker.
Yeah, hello? You're not audible if you're asking question. I think
yes, sir, but I think Manjunath also have left the meeting. So can I ask the question directly to you? Will man manage to create innovative technology for renewable energy sources which will stop the greenhouse effect on Earth?
Yeah. Actually, this is an excellent question, and this is the way in which we have to move. Okay. There are so many ways in which we can have the clean energy. One typical example is the wind, the energy from the wind, ocean waves, and things like that. Another very good example is the hydrogen cells. Okay, they are non-polluting. So there are several other ways in which the non-polluting energy sources exist. Only thing is their viability need to be further explored. The solar energy is the best way to tap, and even in India, all over the globe, there is a very good plan by the governments, India government included, to have the increase in the solar energy, tapping of solar energy. That is the best way, and you can see some of the parts of the country, India has moved like anything in this direction. I don't remember the numbers, but substantial progress has been made in the production of solar energy. Eventually, solar energy, energy from the winds, that is your turbines, and from there, energy from the hydrogen cells and things like that will be the solution rather than going for the polluting energy, from nuclear sources or even from the carbon dioxide sources like the current scenarios. Okay.
Okay, sir. Thank you. And next question is asked by Lean Mariam. And is that Lean Mariam is present here?
Why don't you ask directly the questions? Then you can.
Okay. Okay, I will ask the question, sir.
Yeah.
The question is, in our chemistry textbook, says that sulfur alternative to environmentally hazardous refrigerants like CFCs have been successfully synthesized. Could you please explain this?
Yeah, sure. Actually, the refrigerants that were the freon gases earlier, the chlorofluorocarbons, the ozone destroying compounds has been now phased out, and the new refrigerants has come. I don't remember their chemical, formula. I'm sorry, but at the same time they have been replaced with the old ones, which were having ozone destruction potential, both from chlorine and from bromine. The new refrigerants has already come in. Okay, I don't remember. I'm sorry that I don't remember the exact name of those refrigerants, but then new refrigerants has come.
Okay, sir. Sir, next question is asked by our UL Space Club member, Abhinav B. George. I invite Abhinav B. George to ask the question. I think he is here. Abhinav, please ask all the 3 questions asked by you.
Senator, am I audible?
Yeah, sure. Abhinav, you go ahead.
Sir. So as you have answered the question, is there any gases instead of instead of CFCs? And my other, can we create ozone artificially there rather than it is being created naturally?
Very good, very good, very good, very good question. See, this is what most of the people will think, that we can produce ozone and then liberate to the atmosphere. There are a couple of problems here. Number one, the lifetime of ozone in the lower atmosphere is very less. So if you pump up ozone into the atmosphere, produced at the surface, by the time it gets transported to the upper atmosphere, that is in the stratosphere, it cannot, because its lifetime is very less, because the amount of time that is required to get transported to the stratosphere is of the order of months to years. So it cannot, that is not a solution. 2, even if you do that, what is going to happen is ozone is a toxic gas when it is at the surface. If you inhale ozone, there will be health problems. It's a very toxic gas. So we cannot have production of ozone here and then sending it up. Second is, you can have ozone filled balloons and then they can go. But you should also know the mass of the atmosphere. And the fraction of ozone present is very, very high. And it may not be practicable in reality to fill in, because even if you fill in, after some time it will disappear. So you have to keep on continuously sending these, which itself is a hazardous. So refilling ozone by ourselves is next to impossible. Though practically we may think about it, but there are a lot of other problems that are associated. One is the toxicity of nature, so that you cannot produce at the surface and send it them. Second is the lifetime, that if you give the ozone, produce the ozone here, it will not reach the upper atmosphere, because by the time it will be decaying. Third, you can have directly, through some mechanism, through balloons or through some other mechanism, you directly pump up there. But you should also know what is the volume of the atmosphere. It's enormous, and lifetime even. The lifetime may be of the order of a month or maybe something more. But then you have to keep on replenishing this, which is not practically possible. Okay.
Thank you, sir. Is there any chance of creating artificial plants which can purify the carbon dioxide in a large scale rather than planting normal plants?
Actually, this is a good question again. Why another plant? Even the current plants are doing that. But there is a small problem, because net amount of carbon dioxide that is coming from a tree has to be assessed. Okay, and because during its decay and all the other things, and the place in which that is located is also mattering, like whether it is in the higher latitudes, whether it is in the equatorial region, and things like that. This is definitely a way in which, again, I told you, geoengineering. There, people who are thinking about even plantations and what type of plantations and which latitude. Three things: what plantation, which latitude. Because, for example, if you look at the tree leaves, the tree leaves matter. Tree leaf area, it matter, and the other physiological aspects of the plant also will matter in its carbon dioxide production. So, what type of tree, in which latitude? If you plant an equatorial region, it will be different from the effect that you are seeing in the polar regions. Okay? So, and then finally, this will be decaying. The tree will eventually decay, and which will go in biomass. So that also matters. So you have to have an equilibrium between all these three, and that is part of the geoengineering area. But it is possible. Thinking is in the correct direction.
Thank you, sir.
Any other question? No.
No, sir.
No.
Okay, thank you, Abhinav. Sir, there are three questions from Febin Fershad, another member of UL Space Club. I invite Febin to ask the question. Febin, please.
Yeah, please. Go ahead.
Okay, am I audible?
Yeah, sure.
Yes,
Very
sir.
Okay, sir. First of all, thank you very much. Thank you, because it was a wonderful class, traveling through satellites, satellite orbits, remote sensing, and so on.
Thank you.
My first question is about something related to horoscope and so on.
You are not audible now. Febin, now you are not audible.
Sir, is it clear?
Yeah, now I can hear you. Yeah.
Okay. Astrology and horoscope is the best pseudo for astronomical studies, because it's really astronomical, but it isn't. Scientists say that it won't work, and believers say that it will. The position of Sun, Earth, and others cause seasons and day-night occurrence. But how does the position of astronomical bodies such as Sun and others affect a person's life and calculates his date of birth and others?
Fabin, it's an excellent question, but you are wrong person. Because I'm not an authority to explain this particular thing, because horoscope and astrology and those aspects. There are people who believe in, and there are people who believe that there is enough reason. There are people who don't believe it. So I'm not able to comment on how the horoscope or astrological things will be valid or how they are influencing. Okay, probably I'm misfit to answer that question. But at the same time, let me tell you, as an young child, forget about your astrology. You do your job. Your future is in your hand. You put 100% efforts. It will be fructified. Okay. Because even if astrology is valid, you cannot do anything, because the stars, you are born at that particular time and stars were already there, whatever person it is. So you work hard, you have a determination, you are going to win. Okay. So otherwise, astrology I cannot answer. All right. But good question.
The second question is about clouds. Extraterrestrial life have most of our curiosity catch. Researchers say that there can be habitable planets or celestial bodies inside our solar system itself, including Mars and the recent studies of Venus.
Correct.
But most of them don't have clouds and it's dark around the sky.
Correct.
What happens if there is no cloud, and is there any alternatives which we can make of our own? Is there anything naturally for it?
Very good. To answer your question, actually it's a very lengthy question. Okay, so in the whether life is existing at other planets, life in some form or other might have existed in other planets. People do believe, and there are probably people may be getting evidence. People are looking for evidences whether life existed and in what form. Okay, one of the most important thing of going to other planets and observing other planets is they are actually our past or our future. Okay, it's very important to know that studying other planets, they represent our past or they are going to represent our future. Number one. For example, you look at the Venus or Mars, which are Venus doesn't have much of a thick atmosphere at all, and Mars, which has a very thin atmosphere. At one point of time, it was having much thicker atmosphere in the past, and there are evidences that even the evidences of photographs shows that there may be probably a fluid flowing. That what fluid, whether it is water, whether it is some other fluid flowing, but there were reverse kind of structures existing. Okay. You should also know when you are answering this question, we have something called exosphere on Earth, and there is material that is escaping from Earth. When I say material, it is molecules. Okay, the molecules escape from Earth's atmosphere also continuously. Continuously, molecules are escaping from Earth's atmosphere also, and after maybe millions or billions of years, we are also going to have a very similar scenario, like very thin atmosphere and things like that. So that's why I told the life what you are seeing in Mars today will be our future, can be our future, because we are also gas is escaping. Actually, it is through the exosphere. That is one question. Second is whether life can exist in other planets other than Mars and things like that. Yes, there is an area of research that is going on where people are trying to identify exoplanets. In exoplanet, what they are trying to do is look at the planets which are having potential for life. Potential for life means the temperature should be adequate, presence of water should be there, and one of the more important thing is the hydrocarbon chain, because life forms in hydrocarbon chains. Okay, so people are looking for the places where these kind of environment, which is similar to that of Earth, is existing, and there are several exoplanets being detected. Hundreds of exoplanets are already identified, but whether life exists or not, currently we are not knowing. But people say, the scientists say that there is enough potential for life to exist. What form, we don't know. It need not be necessarily human kind of thing and things like that. The third aspect is you are telling about modification of a planet. This is, no, we should not think about, tomorrow what will happen, day after tomorrow what will happen, 1 year after what will happen, 10 years after. That is actually our policy. Definitely that should be there. But we should not limit to maybe 1 year, 2 year, 10 year, or 50 years. What will happen on thousands of years? There is an area of research that is coming, which is exactly what you are telling. Can we modify another planet? It's called terraforming, that you can search in the net, terraforming, okay, where you can actually start modifying a planet's environment in a limited fashion, something like a football ground, and how that can be nourished, developed, but it will take not 1 year, not 10 years, not 100 years, thousands of years for such a self-sustaining atmosphere to come up. People are thinking in that line, at least not for the entire planet, but for a limited location of the planet. This will be also useful for future, the space travel and things like that. People are also already thinking about that. But no single nation, no single space agency will be able to do this, because the time frame required is of the order of hundreds to thousands of years. Okay, so that means this has to be a collective effort by all global people. But then there is an area of thinking that is going on. You can search. Okay. Fabin, any other question?
Yes, I have one more question. The last one. It's about auroras. I actually don't know what it is, but I have heard that it's the most easily observable phenomenon of effects of Earth's magnetosphere from sky or space. The most striking one of ionosphere. How does it forms, and what's the science behind aurora? What does it indicate?
Very good question. See, I told you in the beginning, the first part of my lecture, that sun emits not only radiation, but it emits particles. They are called solar wind. They are protons or highly energetic particles. These particles come and they go radially outward from the sun. They also come to the earth. While coming to the earth, now you assume a magnet. You have practical, in your classes, you have a bar magnet. You have a magnetic field line that is going around it. You have a magnetic field line, from the North Pole to South Pole. Earth's case is very similar. Earth has a magnet. Earth has a magnetic field, very similar to a dipole, with the, magnetic pole emanating from one pole and then going to the other pole. Now when a charged particle comes, it cannot cross a magnetic field. There is a force called a Lorentzian force. That is, a particle cannot move, a charged particle cannot move perpendicular to the magnetic field. What will happen is, this force will deflect it. Okay. So right at the Earth's geomagnetic equator, and incidentally, Earth's geomagnetic equator is very close to Tumba, where the Vikram Sarabhai Space Center, Vikram Sarabhai has identified, and why that is identified is also because of the geomagnetic equator that is very close to Tumba, where the magnetic field is parallel to the Earth. Now you just imagine a solar wind particle come. It will be trying to cross the magnetic field. It will not be allowed. So it will be deflected. But these deflected things can go along the magnetic field. There is no problem, because along the magnetic field there is no force. And all these particles will go along the magnetic field. Where do they come? They come at the pole, north pole or south pole, where the magnetic field lines converge. While all these charged particles come at the magnetic pole, magnetic north pole or at magnetic south pole, they are coming with very high energy. They collide with the Earth's atmospheric neutral molecules, liberate the energy, and that energy is emitted in the form of light because they come with very high velocity, very high energy. That emission of light, because these charged particles collide with the neutral atmosphere, that is usual air molecules, is the reason why you have aurora. And aurora directly reflects what is the activity that is coming from the sun. Okay, so that is, as you rightly told, it is one of the most beautiful things which you can see. A highly dynamic thing, like a dancing light, but like a dancing sheet of light kind of thing. Okay, it will be there both in the North Pole and in the South Pole, and at times people have even seen at the higher latitude, lower latitudes, when the intensity was.
I'm very happy, Dr. Rajiv, because Febin is one of our boys who keep asking lots of questions in every forum. Not only that, he has answers too. Whenever there is a quiz program, of course, at the end of this also we have a program, he will be bagging the first prize. And to satisfy them, a person like you is available. And we have lost a lot of opportunity this year because of the epidemic of visiting VSSC, LPSC. Otherwise, these boys, girls, would have got opportunity to listen some of you, and maybe perhaps including your directors. That is lost. But then this webinar is giving a very good opportunity, and thank you very much for coming and answering so patiently and satisfying their thirst for knowing things and their imaginary things. Thank you.
Actually, I must thank you because interacting with the kids is very difficult. Because I can interact with the seniors, but interacting with the kids, because kids can ask. Firstly, they don't have any inhibition. They will ask all kinds of questions, and they are not corrupted because they are fresh. So they ask very good questions, and it is often very difficult to convince them either. Okay, compared to the seniors. The seniors, it is very easy to convince, but then I found that kids are asking more number of questions. Number one. Two, when they ask a question to me and when I answer, it is not they are gaining. Actually, I am gaining because it directs me to another line of thinking. Because otherwise, we cannot simply answer the kind of questions which they are asking. So I just talked to my guru. Around 1 hour before, he told exactly the same thing to me. That when I'm talking, I was telling him I'm very much blessed to be your guide due to another scenario. Then he was telling, no, not like that. I'm also gaining when I'm talking to you. So I think that is the scenario, and I really thank you for giving me an opportunity to interact with these wonderful kids. Very nice.
Rajesh sir, we have one more question from Mr. Arjun from M. Prakash.
Yes, you ask.
Arjun, can I ask the question, or Arjun can ask the question? Please, Arjun.
Sir, what if we can put an exhaust to CFC emitting appliances that can convert it to a harmless gas?
Okay. Actually, firstly, this is what we were addressing earlier. The chlorofluorocarbon is used. The freon gases was used in refrigerants and aerosol sprays and things like that. That already get phased out because of the ozone destroying chlorofluorocarbons. Those kind of materials in the refrigerants is already getting replaced or getting almost fully replaced. So that's already done. Your question is how can we do about it, isn't it, Arjun?
Yes. Yes.
Yeah. So already that is phased out. Actually, that was one of the hindrance. You asked another important question anyway. Let me explain to you this way. Way back in the 70s, when Paul Crutzen told it for the first time, nobody believed it because the industries in the world is so powerful that they cannot simply remove the freons because the scientist is telling. Okay, because a lot of money is involved, a lot of plans are being developed, and a lot of things are happening. And second is there has to be a replacement for that. Firstly, you cannot simply remove. Secondly, there has to be a replacement. So it took several years for the replacements to be discovered and to be implemented. But Paul Crutzen and the team of the Nobel laureates along with him, which I told you. They did not stop at that. They continued till there was efforts from the international governments as a consortium to address this very important problem. And that is why Arjun and Rajiv is sitting today. Otherwise, it would not have been possible the way in which we were doing. And definitely beyond maybe another 10 or 15 years, it would have been catastrophic. And we owe our lives to such people whom we never know. Actually, our existence itself is because of such people who were, behind all these things. You understand? Arjun?
Yes, sir.
So, Arjun, thank you. Thank you, Rajiv sir. It was a wonderful session by you. We enjoyed a lot. I want to say sorry to those students who have asked many questions. There was a lot of questions from out of this topic. So they can ask this question to our social media accounts. You can contact us via Instagram account or Facebook page. And we also have given our WhatsApp numbers. So you can ask the question to us, and we will be able to correct the question from the expert to you. So please do it. And sorry for rejecting that question because we have a short of time. So thank you, Rajiv sir. Once more, thank you, sir. It was a wonderful session. I also enjoyed a lot, and it was a new word for me to say about passive remote sensing satellites. I just know about remote sensing, but that term was really new for me. And thank you, sir, for that. Yes, sir. No, I would like to hand over to Shajil sir.
Thank you, Varun. We enjoyed these question answer sessions, and I will say frankly that I also a student along with you, sir, and I started this and recorded everything. I have made my short note also based on your class, because a lot of information you provided here is helpful for me in my classrooms also as a biology teacher, and I really enjoyed that. These are words from my heart, sir. And
thank you very much.
And I think some of these students may get the chance or the opportunity to guided by you even for the research and the academics like that. And I request your advice and support to these students in future also, sir, for them, sir.
Definitely.
Okay, sir. And that kind of, and we also monitoring the development that vigorously they are involving this kind of activity. Even in the organizers are the students. All the
way in which it is conducted, okay? Very nice, very nice. And I also knew that you are serious about it. It is not that simply you are living. Actually, you people, both Kutizar and yourself, were overviewing what the kids are doing, and the kids did a wonderful job. I'm really proud of them. Very nice.
That is the ecosystem we are developing here. That's our dream also. And now we have only 10 or 15, and we have still the 44 students are there, and they are so curious to know. They all are serious to be part of that. And before we leaving, next is our concluding session, and we have some eminent persons sitting here along with us. And I request TP Shashikumar sir to make a reflection on today's class, sir. Welcome, sir. Shashikumar sir. Hello.
Yeah.
Shashikumar sir, are you available now? Okay, it's not.
I think he's not there. He was there until recently. He was there.
I invite K. Jairam sir, the former deputy director of ISRO. He's also part of our UL Space Club, and please make a comment on these. Make your reflection on these today's program, sir. Welcome, sir. Jairam sir.
Thank you, and an excellent session. And in fact, I also, even though I was with ISRO and I was into communication and remote sensing, etc., application part, today I became a real student. And I don't know, I got so immersed into whatever you were presenting and the interaction that we don't know, the time has just passed, We started at 3 o'clock, and now I think it's almost 5. So it was an excellent interaction, excellent presentation. Really so nice to be listening to you, sir. So hats off to you. Thank you very much for the opportunity, and we look forward much more from your side to take our kids, no, in most graceful and say important way forward. Thank you very much.
Thank you, sir. Thank you very much.
Doctor, is Dr. Hegde available, please? Because on 5th, day after is his talk. Only on, sorry, 7th is the talk. Is Dr. Hegde? Hegde was there. I don't know.
Damodar sir is not also available, I think so, sir, due to some problems.
Sir, just a minute, sir. Sir, we have given the links for our Facebook page and Instagram page and our WhatsApp numbers in the chat window. All of you can contact us via that number and that links. And the quiz link for the UL Space Club quiz 20 also given in the chat window. Please use it and please attend the quiz competition. Thank you.
Okay. I think it's concluding the sessions, and that's a vote of thanks. And we are awaiting for the next 2 days in this space week. That is the 5th and 7th of this October. And the first day we have Dr. Y.V.N. Krishnamurthy and Dr. K. Ganesh Raj to speak on the Indian scenario on environment and sustainable development through remote sensing satellites. And on 7th, we have a talk on Indian strengths in communication, navigation, disaster risk reduction through satellites by Dr. V.S. Hegde and Dr. S. Rangarajan. These are the additional talks we have in this space week. And I think all the students will be available here and to interact. And one more interesting thing for these sessions are our 4 student fellows, Bharat Srijit and Adil P. and Varun Mugadhan and Sriram D is sitting along with these great personalities in the discussions. That's the things they are become part of these presenters also. And we are awaiting these things. And next, our Damodaran sir, who has to express the vote of thanks, is not available here. And I hand over this duty to a new student, that is Adidev JD. He's a 10th standard student to make a vote of thanks in this session. Adidev JD, you are requested to make a vote of thanks. Okay.
Sir, am I audible?
Yes, yes.
My name is Aditya JD. I am studying in Saraswati Vidyamandir Nanminda, and I am now in 10th standard. I was added in the UL Space Club group recently, and I had attended almost all the classes of UL Space Club, and this is a big opportunity to me as a student fellow to say the thanks for the faculties. And today's class was fantastic, and all the details was very clear, and even a child could understand each and every portion of the seminar, except some scientific terms and scientific equation, which is categorized to some higher levels. I thank, first of all, I thank Dr. K. Rajiv sir for this wonderful session, and I also thank all the other dignitaries such as Kutti sir, Shadil sir, and also my friends Varunatan, Bharat, Sriram, and Adil, etc. So I here formally says my thanks to all who has take effort to give this class to us. That's all. Thank you.
Okay, thank you, Adidev. And before we leaving, our Shashikumar sir is available now. We want some more reflection from his part, sir. Welcome, sir.
Namaste. I had a call, that is why I couldn't. I broke that sequence of questions were going on, so I was enjoying how Rajiv is answering all of that. Very good, well done. So I think I'm a remote sensing man from Hyderabad.
I know, sir. I know you. Actually, I was a little bit bit worried because when people like you are sitting and I am only addressing the kids. I mean, I was really concerned.
No, people are more concerned about atmosphere, environment than real remote sensing. I think it catered all their questions very well.
Thank you, sir. Thank you very much. Thank you.
I think the basic problem is the ozone generation is very slow, but the depletion is very fast, right?
Actually, ozone has a lifetime in the atmosphere. As you rightly told, it can be getting destroyed in a month's time, even in the Antarctic region, in the stratosphere. That is a big and unless it is, replenished from the equatorial region where ozone production is high, it will not be able to sustain. Polar vortex prevents it during the winter season from entering inside. So that's why it aids the hold. That's also there. You are right, sir.
Okay, anyway, good. UL is doing very good.
Thank you very much. Thank you very much.
Thank you, sir. And we are awaiting for the words from our teacher.
What about Dr. Ganesh Raj? Is he available? Dr. Ganesh Raj? He was there throughout. He's a real remote sensing man.
Yeah.
Okay, I think probably is left.
No, sir, then we want to hear some more the future plans from Kutu sir.
So we have already told about what is in store in the coming week. That is on 5th we have the talk on remote sensing area by YBN Krishnamurthy and Raj. And then we have on 7th the talk on communication, navigation, disaster, etc. by Dr. V.S. Hegde and Dr. Rangarajan, S. Rangarajan. Then on 10th, we have a talk about which I said about viewing the title of the talk is melting ice and climate status from space. That is on 10th. And on 9th, we have a talk by our student Abhinand. So these are the programs which are lined up already. Of course, we have a talk on radio astronomy on 17th by Dr. Rajaram Nityananda, who was in GMRT Pune. And further things are also, we are lining up further things. And things are going very well because of the kind of support, encouragement, and high cooperation we are getting from institutions like ISRO, IIST, PRL, IIA, Indigenous Astrophysics, RRI, etc. So we are very, very grateful for all these organizations for keeping us ticking and making our students excited and curious each day about what is in store for the next week. So this is it. I think further things we'll discuss in the next Saturday, the program. So thank you very much for a fantastic program, Dr. Rajiv, and also for all those who are present. Thank you.
Okay. Thank you, sir. Today we are leaving and we will again rejoin after one day after, and we'll continue. We welcome all the dignitaries to the next coming programs. We'll inform you